Welcome to Digital Dynamics Studio. In this tutorial, we're going to set up and simulate airflow past an airfoil. An airfoil is just a wing's cross-section. Since Digital Dynamics Studio doesn't simulate applications in 3D, it simulates 2D applications in real time. We can set up and simulate airflow past a cross-section of a wing, and the cross-section is called an airfoil, and its shape and its aerodynamic characteristics are critical in the performance of a wing in an aircraft. So we'll be setting up those experiments and talking about airfoils more in a moment. But first, of course, before we can do any demo, we gotta go to the studio and sign in. So if you haven't already, go to www.digitaldynamics.studio. And if you haven't already created a free account, click on Get Started, fill in all your information here to create a free account. And once you've done that, you can click on Sign In and type in your account information to sign into the studio. By default, of course, it puts you in the welcome page, the landing page, which has some information, orientation information, what is a simulation, what is computational fluid dynamics, and the information on where to go next if you're new to the tool, kind of some links on how to get started using the tool, how to learn how to use it, and what kind of simulations you can perform using the studio. If you want to get started right away, you can click on one of these pre-canned simulations here on the left, specifically airfoil past an airfoil, and it'll set up the model and simulation parameters for you automatically, and all you have to do is run the simulation. We're not going to do that here in this tutorial. We're going to set things up from scratch, create our model, and then set up our simulation parameters and perform the simulation. But if you really want us to get started right away, you can click on that button there on the left. But before we get started, we wanted to point out the documentation tab here on the right. This has all kinds of information about what the tool is, what is computational fluid dynamics, what is a simulation, some essential information about using the tool, some other tutorials. Here's a big walkthrough tutorial that you can go through if you wanted to, information about how to create models, geometric modeling, how to use the interface for creating geometric models, simulation, what is a simulation, what are the governing equations, you can see some of them here, what is happening during a simulation, all kinds of information, visualization, how to set up and effectively visualize your simulation results. Specifically, we want to point out the student experiment section. Now, this contains under several different categories setups for what you can do with the tool in aerodynamics, cylinders and shapes, vortex shedding, all kinds of information. Specifically in this case, airfoils. What is an airfoil? What is a wing? What are the important design characteristics? Angle of attack. Here's information about the airfoils. A lot of background information is always suggested experiments, but then it gets into what actually some experiments you can do using the Digital Dynamics Studio, in this case, specifically for airfoils. Things that you can try out and measure and answer some questions about the airfoils and the aerodynamics involved. Suggest that you don't have to do these experiments, but if you want to get started, these are suggested experiments you can do, in this case, for airfoils, and of course, there's other categories, spinning cylinders, vortex shedding, suggested experiments that you can do. So we just wanted to point that out. We're not going to follow along with this document. In this tutorial, we're just going to kind of wing it a little bit and set up experiments from scratch and look at a few different things, but we just wanted to point out this documentation before we get started. The first thing we need to do in any simulation is basically set up the geometry of our problem. Set up your outer domain, the object that you're simulating, in this case, of course, an airfoil. Basically set up everything geometry related to the application you're going to be simulating with computational fluid dynamics, and you do that under, of course, the modeling tab. So we'll switch over there. Since Digital Dynamics Studio is a 2D simulation engine, all the models themselves, of course, are also in 2D. We're not going to cover all the details about geometric modeling here. You can always go over to the documentation modeling to learn all about how to create models and what everything is. We're not going to go, and there's a tutorial, of course, as well, specifically for modeling, so you can follow along with that. So we're not going to go into those details here. We're just going to show you how to create a geometric model of our airfoil and step that up for simulation. So back here in the modeling tab, by default, it creates a cylinder for you in case you want to do airflow past a cylinder. We're not doing that here, so we need to switch it to an airfoil. And the good news is that the modeling tool within Digital Dynamics Studio can create airfoils for you automatically. So let's reset our model to an airfoil model as a starting point. There we go. So here's the airfoil. In Digital Dynamics Studio, we automatically allow you to create NACA 4-digit series airfoils. The nose are been around since I think the 20s for quite a while. It's a series of airfoils that NACA, which is a precursor to NASA, had developed a long time ago, and the shape of the airfoil is determined by these 4 numbers. What we see here is in MACA 4412 airfoil, and those numbers determine the shape of the airfoil, and we'll see that in just a second. But by default, in a simulation, you have the object you're simulating airfoil around, which you see right here, which is the airfoil. But you need to tell it where to model the fluid around the airfoil, and that's the outer domain. What you see here is that rectangle. That kind of limits where the simulation is going to happen. We're going to be simulating fluid flow within this box here, basically. The fluid will be coming in through this left boundary. You can check on boundary numbers to see what they are. Fluid will be coming in through the left boundary number 2 and flowing over the airflow, which as you can see here is boundary number 1, and leaving the domain through the right boundary here, which is boundary number 4. About the tops and bottom boundaries in number 3, and we're going to allow the fluid to slip along that boundary in the x direction but not penetrate that boundary. Basically, it constrains the flow within the computational domain, which is what we see here. So this is kind of like a wind tunnel setup. You can think of this as a wind tunnel. Fluid is going to be moved from left to right through this channel here, and in the middle of the channel we have our airfoil. So the default model, let me see here, when we get reset airfoil, is fine for simulation, the outer domain. You can make that bigger if you want, or even smaller if you really wanted to, the outer domain, but this is fine for our purposes here, this size here, where you can see here this number, the inflow is at minus 10 units to the left, 30 units to the right, and 10 units top and bottom, so the width of the domain is 20. But let's your half boundary numbers and zoom in on our airfoil, and we'll look at that a little bit more closely. So you can see for airfoils in Digital Dynamics Studio, they have some special controls here. You can see you can change the length by moving these ones here on the right. You can see the default length is 5 units in length, and that's fine. We'll just leave that alone. 5 units is just fine for our simulations. You should take note of that. You want to know that the length is 5 when you do Reynolds number and lift and drag coefficient calculations. You need to know that value, but 5 is fine. We'll just leave that alone. These controls in the middle control the shape. Like I mentioned before, the NACA 4-digit series has 4 numbers, which designate the shape of the airfoil. And you can grab and move these controls around to change that number, to change the shape. So 4, the first number 4 there, is the amount of camber in the airfoil. You can see that the airfoil bends. Most airfoils have some kind of bend to them. And the first number, you can see it's changing as they go up and down, controls the amount of bending in the airfoil. That's called the camber. So you can, a lot of bending, and 9412 has a lot of camber, a lot of bending. A 0012 has 0 bend, it has no camber. It's just a straight symmetric airfoil. But we'll do the 4412 airfoil, that's just fine. The second number determines where along the airfoil this maximum camber is. It could be closer to the nose or closer to the tail. Sometimes you can create something like weird shapes that you don't want to deal with, but for the 4 means that the maximum camber is at 40% along the airfoil from the nose, and that's fine. We're going to do a 4412 airfoil. And the last 2 digits is the thickness of the airfoil as a percent of chord length. So the thickness of the airfoil is 12% of the length of the airfoil. And you can grab these controls up here on the top and change that thickness if you want to. A very thin airfoil, very thick airfoil. But we're going to do a 4412 airfoil, which is a very common, very standard shape. So we'll just leave it just like that. A few other things we want to control. This is the center of the airfoil, the entire airfoil as an object. It's right here. And we can move that around if we want to. We're not going to. We want to leave everything centered at coordinates 0, 0, right in the middle of the domain. But you could move it around if you wanted to. The main thing we want to do is angle of attack, which is the angle of the wing with respect to the motion of the airflow. And remember, we said the flow is going to be coming in from the left and moving to the right and leaving the domain at the exit right here on the right. So the flow is aligned directly with the x-axis in our setup. It's going to be moving exactly in the x direction with the velocity of 1.0. The speed of the flow in the y direction will be 0. There's no overall motion in the y direction, at least on the inflow boundary. So the flow is aligned with the x-axis. So there's a critical angle used in wings and airfoils called the angle of attack. And that is the angle of the wing with respect to the main fluid flow direction. What is the angle of the wing? Well, the angle of that airfoil is defined as the line from the airfoil's tip right there to its tail right there. So in this case, actually, the line right here along the x-axis is the wing's center line. Chord line, actually. The camber line is this dotted line here. The chord line is the line from the tip to the tail. So right now, as you can see, it's a 0 angle of attack. They're totally in line with each other. To rotate the airfoil, you can just select anywhere on one of the curves and just move it up and down. So there you can change the angle of any model by just grabbing it and rotating it around. But you can see that the actual angle here printed on the screen in the middle there. So we want to do, for this tutorial, we'll just do 10 degrees. You can do a smaller angle or higher angle. But for this tutorial, let's start with 10 degrees. So we'll rotate it to 10 degrees. And you can see that's jumping between, I think, 2.5 degrees every time you move it. That's because the grid snap over here was on. If I turn off grid snap, then I can do any degree that I want. But with grid snap, it kind of keeps the numbers within a specific range, so you can get exact values. So we'll do 10 degrees. So you can see here the wind is coming here, aligned with the x-axis, and the wing is up here at 10 degrees angle between the tip and the tail. So this will be a 10 degrees angle of attack simulation. So this is pretty much it for our model. We have the geometry that we want. We have our NAC 4412 airfoil at 10 degrees. The outer domains are correct the way we want them to be. The boundary numbers all look good. The airfoil is boundary number 1. The inflow boundary on the left is where the airflow is coming in, is boundary number 2. The tops and bottoms are number 3. And the outflow boundary on the right is boundary number 4. So this model is ready to go, and the next step is to go over to the simulation tab and set up and run the simulation. So now that we got our geometric model traded for airflow past an airfoil, if you remember, it's a NAC 4412 airfoil at 10 degrees angle of attack. We can go ahead and carry out the simulation by switching over to the simulation tab, as we see here. The first thing you need to do is load your model. Now this, of course, you push the load button to get going, and any of your previously saved models are here, and you could load them if you wanted to, but we're going to load the model that we just are editing in the modeling tab. So if you do load current model, that will load the model that's currently being edited in the modeling tab. So let's go ahead and do that. And there we go. A lot has happened. Actually, since when you push that button, a lot has taken place. Import to the model, and you can see it's represented here by the blue boundaries. We see the model of the airfoil and the outer domains. And what happened is that it filled the interior of the computational domain with a mesh, an unstructured computational mesh. And that defines where the fluid is, where the simulation will take place. The numerical method itself can't happen without a mesh. The mesh is the backbone of the simulation. You can see basically divided a domain up into many, many, many small triangles. And these triangles, as you see here, each triangle is called an element, and the corners of the triangles are called nodes. And this is just the initial unstructured mesh. that was generated just to get things going. The digital dynamics simulation engine uses a solution adaptive technique. And that basically means that this mesh structure and the member nodes, the rotation of the nodes, the elements are all going to change continuously throughout the simulation so as to model the features of the flow that are developing around and behind the airfoil as accurately as possible. Where things are happening as a vortice or a strong change in velocity, it's going to put more nodes and elements in those locations to capture those features better. In other locations where not much is happening, away from the airfoil here, it'll just allow a low refinement, bigger triangles and less dense population of nodes in those regions since, accuracy or the resolution of the mesh isn't as important in those locations. But this is just the initial mesh, just to get things going, to allow the simulation to proceed. So once the mesh is loaded, the first thing you need to do is change these simulation parameters. First is simulation type, and we're just going to choose the default incompressible. That means we're solving the incompressible Mavir-Stokes equations, which govern the fluid flow for most applications in the world. And it's two-dimensional, and this is all a 2D Nash, 2D simulation, modeling simulation past airfoil in 2D, so it's the two-dimensional incompressible Mavir-Stokes equations. I'm not going to cover those here. You can look at my documentation under simulation governing equations to see what those equations are. It talks all about them and what's being modeled and what they represent. They're actually right here. These are the equations, the governing equations that we're solving, which determine how the fluid flow behaves in our simulation. But we're not going to really go into details about those here, but that's what's being simulated, those equations. Time subsize, what's going to happen is when the simulation progresses, it's going to compute the solution, which are velocity and pressure variables. Velocity is a vector, so there's a x and a y component, so that's 2, plus pressure, that's 3 degrees of freedom, 3 variables at each node of the mesh, at each simulation frame. And it's kind of like a movie where, a movie is constructed of a series of images that when played back together, show here what's happening in the movie. Pretty much the same thing happens here. We're going to compute the solution at a bunch of individual frames, and that could be played back to see how the fluid flow behaves. And the separation in time between each computational frame, each simulation frame, is the time subsize, 0.1. That default value is fine for the simulation. We're not going to really change that here. You can look at the documentation further about VAT or any of these variables. But the default time subsize of 0.01, which is the simulation time between individual frames that are computed, is that value. Next I is viscosity. And that's right here. The default is 0.005. And we'll just leave that for this simulation. Viscosity helps define the Reynolds number. The Reynolds number is a non-dimensional number, which is the main parameter used to characterize these kinds of incompressible flows. And it's a non-dimensional number that you can calculate. It's the inflow velocity, which will be 1.0 for the simulation, times a length scale. And for airfoils, we use the length of the airfoil as the length scale. And if you remember from the model, that length is 5.0 right there. So that's the length scale divided by viscosity, which is 0.005. Or you could change it if you want, but we're going to go with 0.005 for this simulation. So if you have a velocity of 1, a length of 5 divided by 0.005, the Reynolds number for the simulation is going to be 1,000. That's fairly low Reynolds number. I mean, it's fairly viscous. A low Reynolds number, the viscosity is fairly high for these kinds of flows, but it's good we'll use that for our initial simulation. It's a good standard setup for an initial simulation. The next thing to look at are the boundary conditions, which are defined in here. Remember, there is showing you 4 boundaries, and we have to associate a boundary condition to each of the boundaries. Those 4 boundaries, remember, we assign those in our model. Boundary 1 is the airfoil, 2 is the left inflow boundary, 4 is the right outflow boundary, and 3 are the tops and bottoms of the domain. So those are represented here in the boundary conditions. So boundary number 1, we're just going to assign the default no-slip boundary condition. Basically what that means is that the velocity of the fluid on that boundary must match the velocity of the object. It sticks to the object, so the velocities must match. And since the airfoil is stationary, it has a velocity of 0.0, so the fluid velocity along the airfoil should also be 0.0, and that's what the num-slip boundary condition enforces. Boundary 2 is the inflow, so we'll just give it the inflow boundary condition. That's where the fluid is entering the domain at a velocity of 1.0. You could change it if you want, but usually we like to use unit dimensions that are close to 1.0 for these kinds of simulations. So the inflow velocity, the free stream velocity in this application will be 1.0. The tops and the bottoms of the domain will be an x-slip boundary condition that allows the fluid to slide along the boundary in the x direction, but not penetrate the boundary. It enforces a wide velocity of 0.0, and that just basically prevents the fluid from leaving the domain along those side boundaries. And boundary number 4 is here on the right. That's the outflow boundary where the fluid can exit, so we'll just assign the outflow boundary to that boundary. So that's pretty much it for the boundary conditions, and in this case, the default. You should definitely double check the boundary conditions all the time before you start a simulation, but in this case, the default boundary conditions are just fine for this simulation. Normally, there's a set of advanced parameters here. Normally, you don't have to deal with those, but in this simulation, I'm going to increase the max mesh size limit to a little bit higher. Basically, since it's an adaptive technique, the mesh is going to be changing itself, growing in size, probably growing in size throughout the simulation as far as the number of nodes and elements in the mesh. And the algorithm enforces a maximum mesh size limit of 10,000 elements. So a max default value of 1 corresponds to a maximum mesh size of 10,000 elements. I'm going to change to 1.5, which will allow the maximum mesh size to be 15,000 elements. A little bit bigger, a little bit more refined, will capture the features a little bit more accurately. Usually a bigger mesh means the solution will be a little bit more accurate. It'll take a little bit longer to compute since you're computing a larger mesh, but it'll be a little bit more accurate. And correspondingly, I'm going to increase the mesh refinement factor a little bit. You can read all about these parameters in the documentation. There's a section under simulation, interface, simulation parameters. All of those variables are discussing details here, so please refer to that for more information. So we're pretty much ready to go. The next step is to go ahead and run our simulation. We can run the simulation by toggling this person icon here in the lower right. This controls if the simulation is currently running or not. If it is in the standing position, the simulation is either not started yet, hasn't begun yet, like we are right now, or you've running the simulation, but you paused it. A certain number of frames had been computed, but you're pausing the simulation. This is basically a toggle switch on or off and determines whether the simulation is currently running or not. So to run the simulation, we'll just push the person icon and change to the running state. And you can see there it goes. You can see variables are being calculated. Something is happening in the window here. The simulation is being carried out and we're generating results. Then you see here in the bottom, the timeline, a number of frames are being computed. Brought a 900, 1,000 frames, probably 1,100. You see a bunch of frames are being computed. I'm going to stop the simulation or pause it right now by pushing on the person icon again. So when the simulation was being carried out, the simulation engine in the background was caching each simulation frame in memory or on disk. We're not sure what it does. It's caching the results internally so that you can play them back after they've been computed at any time by pushing on this playback button here in the middle like that. So it's not running the current simulation, it's just playing back what we just computed from the internal cache. You can toggle that on and off at any time you want, or you can step back one frame or push this button to go forward individual frames. But for now, we'll just let it run continuously. Next thing you might want to do is change what you're seeing on the screen. Right now we're seeing, if you go to the display properties by pushing on this button here, you bring up the display panel. We're seeing a mesh and the velocity vectors. You can see the mesh. You can see the adaptive algorithm happening here. You can see how the mesh is changing its structure and density and sizes to follow the features of the flow. This is done so that as much as possible, we can ensure high accuracy of the results everywhere in the domain at all times. You can see it basically the adaptation extends throughout the entire computational domain. Okay, let's zoom in here. So that's the mesh. You can look at that if you want. Or velocity vectors. These show at every node in the mesh room, and that's where we're calculating velocity and pressure at each frame, or at the nodes of the mesh. And here you can see the velocity vector at each node of the mesh. Now, the direction of the vectors shows the direction of the flow, and the length of the vector denotes the speed of the flow. You can see that the vectors are very short in here, so the speed of the flow is very well here, and it's much higher out here where the vectors are longer. That's velocity vectors. We'll talk about the actual results in a moment once we just quick cover the displayed properties. We are going to cover the display properties in great detail. You can read about them in the documentation and other tutorials. You can look at pressure. Just a quick overview. You can look at pressure. Blue is low pressure. Blue is low pressure. Greens and reds are higher pressure. You can see this difference in pressure across the airfoil, the low pressure on the top and the higher pressure at the bottom. That creates the lift that keeps the airfoil in the air, as you would expect. Vorticity is good we're able to look at in these kinds of flows. It's not necessarily the spinning of the flow, but more of the turning of the flow. Turning of the fluid. Kind of red is a turning of the flow in a counterclockwise direction, and blue is the turning of the flow in the clockwise direction. And you would turn on velocity vectors, you can correlate those two, the turning in one direction versus the other direction, and how it relates to vorticity. You can visually see that here. Speed is the speed of the flow. Blues are the lower speeds, and the reds and the yellows are the higher speeds. You can see that here. Normally we don't look at speed too much. It's not super intuitive and doesn't really tell us much about the flow, but it's another variable you can look at. And then there's particle traces, irregular particles, places massless particles, thousands of them into the domain at all locations that can like dust in the wind or snowflakes or something like that. And they just get carried with the flow, and by observing their motion, you can kind of see how the flow behaves. You can get a good overall picture of the fluid flow by looking at these particle traces. And finally, you can look at regular particles, which are a little bit like streamlines. They release, I'm going to turn it off, release particles in a row, and instead of everywhere in the domain, it just releases them in these rows coming from the inflow boundary and the flow around the object and behind it. And again, it's a good way to visualize the flow and get a good picture of what's happening, in the flow. You can definitely see the wake and the vortex shedding that is happening behind the airfoil in this situation. One final thing we want to highlight are the forces that are generated on this airflow by the fluid. Along with the fluid variables within the computational domain, we're also calculating the forces on the object, in this case the airfoil, that are also generated by the fluid. There's a force in the y direction, up and down, which is lift. As you can see here highlighted in red, red represents the lift generated on the airfoil by the fluid. And blue is the drag force, that's the force in the x direction generated on this airfoil. We can see that due to the vortex shedding behind the cylinder at this low Reynolds number, you're getting oscillation in the lift forces, as you can see here. That's 100% due to the vortex shedding that's happening behind the cylinder. If this was on your aircraft and you were flying with this wing under this condition, you'd probably feel that as a little vibration in the aircraft. But that's kind of what these graphs represent. There's other things you can look at. Performance, the blue is the size of the mesh, the red and brown here are how fast the simulation proceeded. There's some convergence information here as well, but no, in this case, we're just going to look at the forces that are generated on the airfoil. Red being the lift and blue being the drag, as you can see here. Let me turn now for now. So let's talk about what happened in the simulation. What do the results look like? What do they mean? Let's look at velocity vectors. In this case, the Reynolds number, as we talked about, is fairly low. Reynolds number 1000, which means there's a lot of viscosity in the flow, and since the viscosity itself is fairly high, 0.005 is actually a fairly high viscosity, and that results in a low Reynolds number. So what does that mean? It means the flow is definitely separated the flow is not following the contours of the airfoil. As you can see here, the fluid is actually going the opposite direction. It's going backwards a little bit here in the wake of the airfoil. So the flow is definitely separated. In aircraft flight terminology, the wing has stalled. The flow is detached from the airfoil, so it has stalled. And you can see these vortices are developing in the wake of the airfoil. They form, as you can see, and then they kind of detach from the airfoil and then get carried downstream all the way out to the exit of the domain. They kind of go all the way downstream. Here they go. You can see they're all the way downstream until they leave the domain. So this is vortex shedding. This is a very common behavior in kind of low Reynolds number flows, this vortex shedding behavior. It's super common. It happens everywhere. But in this case, the airfoil has stalled. The flow has separated. And we're getting vortex shedding behind the airflow. So this is not a good flight condition. You wouldn't want to be flying your aircraft under this flight condition. But in any aircraft, you'd be at a much higher Reynolds number than this low Reynolds number 1000 condition. In the next step, we're going to change the viscosity and do a higher Reynolds number simulation and kind of see what that looks like. So now in this next part, we're going to change the viscosity and thus change the Reynolds number and do a higher Reynolds number simulation. So we're done with this simulation. We want to, we don't need it anymore. We're going to delete it. So to reset everything and start again, you push on the X, which is the reset simulation button. So you click on that, and we're back to where we began. There's their initial mesh. All the cached frames are deleted from the background, and we can go ahead and change our simulation parameters again. So to real aircraft, like a real airplane, either a light airplane or a commercial airline or something like that, the actual Reynolds number will be very high, tens of millions for a Reynolds number we simulated in 1000 in Reynolds number 1000 in the last simulation. But in a real situation, with real air viscosities and everything, the Reynolds number would actually be much, much higher. So let's kind of simulate that condition. Let's change the viscosity to something lower, which means that the Reynolds number will be much higher. In this case, roughly 2 orders of magnitude higher. In those kinds of flows, there are problems that arise. Number one is called turbulence. Not turbulence like you would in flying in an aircraft cross country and you hit some bumps and turbulence. That's not the turbulence that we're talking about here. It's just that the fluid becomes very chaotic and unstable at higher Reynolds number, and the Reynolds numbers and the features of the flow become very, very small in certain areas, almost microscopic. That's called turbulence. And like I said, the features become very small and very microscopic, and meshes like this have a very difficult time. They just can't capture all of those features of the flow, those very small, chaotic, turbulent features of the flow at high Reynolds number. So the best we can do is just model them through relationships between their variables, the singulature variables we do know about, and the turbulent energies and what effect they have on the flow. So for high Reynolds numbers, we're going to turn on the turbulence model, which is basically required. It's a very simple turbulence model. It's a large eddy turbulence model, an LES model, which is fine for these kinds of flows that we're doing here. If you're in Boeing and designing a real aircraft, you'd use a different Stirrup-Hoods model, but for our purposes here to see what the flow looks like and do our analysis, so this kind of turbulence model is just fine. So we'll turn that on for this higher Reynolds number simulation. For the simulation, the boundary conditions are exactly the same. We don't have to change anything there. I am going to change the max mesh size limit. Just let it go a little bit larger, since it'll be much more the flow will be much more complicated. There'll be a lot more smaller features in the flow in this situation, so I'm going to allow the mesh to grow to 20,000 elements in this situation. 2.0 corresponds to a 20,000 mesh size limit. So we'll set that there. And the flow is going to be much more complicated. There's going to be a lot of things happening, a lot of smaller features in the flow. To handle that, I'm going to reduce the time step size to 0.05. That'll just be a little bit more accurate when we're solving these kinds of flows. So everything's set up there. The next step is to run the simulation. So we can push the person icon again and run that simulation. And let's look at vorticity. There we go. You can see that the simulation itself is running slower. For a couple of reasons. Number one, the results are going to be more complicated. There's a lot more work that the simulation engine has to do to calculate the results. And number two, the mesh itself is going to be a little bit larger than it was before. And because of that, it's going to take a little bit longer to compute these frames. You can see right here, Romy at frame 300 in the simulation. Let's turn lift and drag curves again so you can see those. There we go. So we'll let that run for a little while. This is probably good enough. Let's stop the simulation here. There we go, and play it back. So here you can see in this simulation, let's turn off vorticity. The mesh is much larger. You can see there's a lot more finer features. But the flow generally does stay attached to the airfoil throughout over. Remember, we had this large separation zone before on the top of the airfoil. Here, there's a little bit of separation at the very tip. That's probably because our viscosity is a little bit too high, and to some extent, the size of the mesh in those locations, there's very thin boundary layer features along the boundaries in this situation, and the adaptive framework is doing the best it can to add small elements in those locations, but it's just not small enough to capture the boundary layer accurately. The size of the mesh will have to be much smaller than this in these kinds of simulations. So the mesh is a little bit thicker than it should be around the airfoil, and because of that, we are probably getting more separation here than we normally would. The separation is probably not realistic. It's just the fact that the mesh that we have just can't get small enough to capture the boundary layer in these regions. But it's pretty close. The flow is very attached. It's fairly attached. And we just have a little bit of separation here at the tip with some vortex shedding happening within the wake of the tail of the airflow. And you can see that the lift is fairly high. It's a good number, about 3.0 under this condition, and the drag is fairly low, about 0.15 or something. Let's even pause it here at the end, jump to the end. You can see that the drag is about 0.14 and the lift is about 3. So those are fairly high lift to drag ratios, what you would expect for an airfoil flying at 10 degrees. So again, it's not as accurate as it could be. Like I said, we could have more elements in the more smaller mesh, the more refined mesh in the boundary layer, and then the separation zone probably would go away. But it's doing a fairly good job of capturing the results that you would see airfoil past an airfoil at this high Reynolds number. In the next part, we'll redo the simulation again, set it up and review it again, but change the boundary conditions somewhat so that we can capture these kinds of flows past airfoils even more accurately with using even less of a simpler mesh. We'll talk about that in the next part of the tutorial. So in this last simulation, if you remember, we had a very low viscosity, which results in a high Reynolds number. We turned the turbulence model lower the time step size, did the best we can to capture these kinds of high Reynolds number of flows. Turn off this vorticity. Like you said, there's some issues with it. It tries to put a bunch of small elements near the boundary to capture the boundary layer features accurately, but it's very difficult. The mesh is large and it's very difficult, so it probably didn't do the best job of capturing the true aerodynamics for this kind of airfoil that had Reynolds number. If we look at the performance graph, you can see that the mesh did go up to 20,000 elements. Remember, the advanced parameters, we set next size limit of 2, which corresponds to 20,000 elements. The nets, where it's capped, the next size isn't allowed to grow any larger than that. If we change that to 3 or 2.5, then the size of the mesh as represented by this blue graph would have got larger and would have been a little bit more accurate. But these are expensive simulations that ran fairly slow. The red graph is representing how fast the simulation ran, which in this case on my machine here was even about 9 frames a second, which is not bad, but these are expensive simulations. In our case, if we're just students studying airfoils, we don't really care so much about bombulaires and details. We just want to get lift and drag coefficients for various airfoil shapes at various angles of attack. So let's set it up just to do a simpler calculation that is doing just that. Just give us good lift to drag coefficients or values for our airfoil. So let's stop and reset the simulation and set up a new simulation. Okay, in this simulation, we're going to change a few things. Let's see. Bailey the boundary condition. Remember, we applied the no-slip boundary condition on the airfoil, which set a 0 velocity on the airfoil. And then the free stream velocity, remember, is 1.0 right here. And the transition between a velocity of 0 and the free stream velocity of 1.0 goes over a very small distance. It's called, like I said, the boundary layer. And it's very small. In real aircraft like this, it's basically almost microscopic. And that's why you have such a problem with those kinds of flows, high Reynolds number flows, because the mesh, it'd be very hard for the mesh to capture the boundary layer accurately for those kinds of flows. But that's a detail of the boundary layer. Yes, it's super important. You want to know what's happening with the boundary layer, but if you're just looking for a what does the fold look like? What is the lift value? What is the drag value for the airfoil at different angles of attack and different shapes? One thing you can do is just ignore the boundary layer, and we can do that by applying a slip condition instead of the no slip condition. Now, this is a special dominant condition, the slip condition. It will allow the flow to slide along the boundary, whatever its shape is, and it'll allow the flow to slide along the boundary, but its velocity will not be 0. It'll be something. The only condition that we're applying is the flow cannot penetrate the boundary. So the velocity of the fluid in the normal direction along the airfoil will be 0. We can slide along the boundary, but it can't penetrate the boundary. And that's basically ignoring the boundary layer. For this analysis that we want to do here, that's just fine. We don't really care so much about the boundary layer. We just want to see what the airfoil looks like around the airfoil and calculate lift and drag coefficients. So we'll apply the slip on a condition on the airfoil to account for that. In this case, since the boundary layer will not be modeled as accurately as it was before, we can go back, reduce these mesh size limits back to 1. The mesh isn't going to be nearly as large in these simulations since it won't be throwing so many nodes and elements in the boundary layer along the airfoil. In this case, the mesh will be much smaller and the simulation will be carried out much quicker. Let's reduce the viscosity a little bit. Since we're covering the boundary layer, the viscosity doesn't really matter as much. So we can decrease that a little bit. We'll leave the turbulence small on in this situation. You probably don't exactly need it in this when you have the slip boundary condition turned on, but let's leave it on for now. And then reduce the time set back to 0.1 since they're not. Is it going to be as much things changing in the simulation as it was before? So we reset those conditions and we can run the simulation. There we go. And let's look at velocity detectors. There we go. So as you can see, it's a much simpler results, steadier results, which is what you want. If you're flying your aircraft, cross country, you don't want to hear these vibrations and what's happening with this vortex shutting, which that's not really physical what happened. This is more of what you would see in a real aircraft. You see that the velocity vectors are, and I'm going right over the aircraft, very smooth. There's no separation here, no separation zone. This is, even though we're ignoring the boundary layer here, this is more typically what you would see an airfoil pass an airfoil under normal conditions. A little bit of startup more to see there just because of startup, but after a while becomes steady. So yeah, in general, the flow will be steady around your wing and your airfoil as you're flying your commercial airliner across the country. Hopefully the flow will be steady over your wing. And you can see here is the lift and drag. Lift in this case of 4.18 and the drag of 0.07. That's probably correct. So let's mark that down. You should write that down. So for 10 degrees angle of attack for our NACA 4412 airfoil, the lift was 4.18 and the drag was 0.0745. And it's steady, as you can see that the curve is pretty much horizontal. There's no oscillation or anything in these lift and drag curves, which means that the flow is steady. There's no point to calculate the simulation further because it will be calculating the same thing over and over again. So once the flow becomes steady, you can pretty much stop your simulation like we have it here. Let's look at a few other variables. You can see that the mesh is pre-course. There's just the flow is so steady and smooth going over the airflow, and not much is changing. The adaptive features of the simulation engine didn't have to do much work to follow the features of the flow. A coarse, small mesh like this, the size is 1,816 triangles elements. It's a fairly small mesh, but that's accurate enough to capture these features. Let's look at vorticity. You're not going to see much there. There's not much. The flow is fairly smooth. There's not much turning of the flow. A little bit here at the tip of the airflow, but not much is happening there. So vorticity isn't going to show much. Pressure is a name variable that you want to look at in these situations. Let's play with that a bit. Let's turn off the mesh. 5. Okay, so pressure. So you remember pressure blue? The blues are the low pressures. In this case, the blue is, it's for little value. And the reds are the higher pressures. So if you have a higher pressure in the reds here in the orange on the bottom of the airfoil, and blue and green lower pressures at the top of the airfoil, that difference in pressure is what creates lift. The force, this red curve here, the force that keeps the aircraft up in the air. You're at the high pressure at the bottom, low pressure at the top, and that difference in pressure keeps the airplane up in the air. So that's where lift comes from when you're in an aircraft. Another way we can visualize it, let's go back to irregular particles and play the simulation. Let's turn off pressure. Actually, here you can see that the flow going around the airfoil is fairly smooth. It's very fast over the top of the airfoil. If you remember from Bernoulli's equation, as the flow speeds up, the pressure goes down. Number of pressure here is very low, which probably means that the speed of the flow is very high there. And high pressure here means the speed of the flow is slow due to Bernoulli's equations. Bernoulli's relationship, which you can study here if you go over to documents, suggested experiments, ergodynamics, Bernoulli's principle, and you can actually study that phenomena using Digital Dynamics Studio. But going back here, so this is what airflow past wing or wing cross section normally looks like as a plane is flying over, flying up in the air. This is what the airflow normally looks like in such situations. So next we can try a few other things before we wrap up this tutorial. So let's try that next. So one other thing we might want to consider, look into, is what's the effect that angle of attack has on the lift generated on the airfoil. Normally higher angle of attack that the airfoil is flying at, the more lift is generated. So let's try to measure that relationship. So to change the angle of attack of our airfoil, this is at 10 degrees. To change it's very easy. We just go back to the model and change the angle. So let's try 0 degrees angle of attack just to start out with. So we change the angle to 0 degrees, go back to simulation, load the new model. So we have pretty much the same mesh, the same kind of mesh, but now the airfoil is at 0 degrees angle of attack. And to run that, we run a simulation. I said that I turned the turbulence model off, and these simulations just help things out a little bit. That's why that warning appears, just giving you a warning that you're running a high Reynolds number simulation without the turbulence model. But since we are applying slip condition along the airfoil, that's totally fine. So there we go. Now it's pretty much steady results when you look at pressure again. There we go. So we still have about 0 degrees angle of attack. We still have a low pressure region on the top of the airfoil, and it's so higher pressure at the bottom and not as high. You can see under this condition we have a lift of 1.27 and a drag of 0.00508. You might be wondering, well, it's an angle of attack of 0. Why is there still lift being generated? And the answer is, of course, is that the airfoil has camber. It has some bend to it. If the airfoil did not have a bend to it, was a symmetric airfoil like here, then we would expect there should be no lift generated on the airfoil at 0 degrees angle of attack. But this is a 4412 airfoil. It has a bend to it, and that bend causes lift to be generated even at 0 degrees angle of attack, as we see here. So remember at 10 degrees, though the drag was about 4.2, now at 0 degrees, the lift is 1.27. You can try something else. Let's reset the simulation. Let's try 5 degrees. There we go. Go back here, reload that, and push that person I found again to run that simulation. And there it goes. And let that run for a while. You know, there's always some nessiness at the beginning of the simulation, but things usually steady, dampen down after a bit. So there it goes, and let it reach a steady point. There we go. So you can see at 5 degrees angle of attack, lift is 2.74. That's pretty much almost double of what it was at 0 degrees angle of attack, but roughly half of what it was at 10 degrees angle of attack. You do it again, go to the modeling. Let's try, 7.5 degrees angle of attack. Come back here, load the mesh and rerun the simulation. And after a while, no pressure again. I'll try off the mesh. Let's try on some particles. Let me reset pressure since this is a different simulation. There we go. So at 7.5 degrees angle of attack, let me change the pressure value. The lift is 3.51. So you can repeat this kind of calculation, change angle of attack, compute the lift value. These are raw lift and drag values, not coefficients. If you go over here to documentation and then governing equations down here, it talks about lift and drag coefficients. Those are undimensional representations of lift and drag. We're not going to, calculate those here, but you can. But you could if you wanted to, since these are raw lift and drag values. But basically what we're interested in right now is the relationship between the angle of attack and lift. So you can go back, try different angles. You do a negative angle. Okay, let's try minus 5 degrees angle of attack, load, and simulate that. So you can go back and forth and try all the different kinds of angles of attack and calculate lift values for all of them, and then create a graph of a lift generated versus angle of attack. See, as here now we got negative lift, since we have a negative 5 degrees angle of attack. We're actually generating a negative lift. We can do 12 degrees. Let's try 12.5 degrees angle of attack. We'll reload it and resimulate the condition. So you can try that for a bunch of different angles and come up with a lift value as corresponding to the angle of attack, and it should be a linear relationship. If you draw the graph, it should be a straight line pretty much. And you can browse the web. What is the lift and drag values versus angle of attack for an airfoil, and even if you want specifically a 4412 airfoil, and you should see a linear relationship between the two. That's how an aircraft flies. The pilot's flying the aircraft. He wants to go up. He pulls back on the yoke, and that doesn't push the airplane up. All that does is change the angle of attack of the airfoil with respect to the wind. And as the angle of attack gets higher, you get more lift. The aircraft is going to rise. The pilot wants to descend and go down. He pushes the yoke forward, which the effect of that is it lowers the angle of attack. You have less lift on your aircraft, and then it starts to descend. So it's this relationship between angle of attack and the lift that's generated is how aircraft fly in the air. That's how pilots are able to fly aircraft. So you can study those kinds of things here using Digital Bananac Studio. But we should note that only goes so far. Once the angle of attack gets too high, let's say 50 degrees, it starts to break down, and will separate, and the aircraft will stall. So at this super high angle of attack of 50 degrees is not realistic. You'd be falling from the sky in reality if you're under this condition. But what's happening here is, adjust the visualization a bit. You see the flow is separating. If you look here, let's turn off the mesh. If you look here, you see flow is separating, that it has stalled. It's still attached to the airfoil way too much. This is not really very realistic for this angle of attack. The flow should be fully separated, probably from the tip here. the fact that it is so attached to the flow, at least to this point here, is because the slip bounding condition is not a physical boundary condition. There would be a boundary layer in reality, and that boundary layer will cause the air to separate from the airfoil and stall much earlier than this case of 50 degrees, probably around 20 degrees, 25 degrees, the airfoil will stall. So this linear relationship between lift and angle of attack really only goes up to, say, 20, 25 degrees, depending upon the airfoil type. There are 50 degrees. You can see that it's still very attached. And that's basically because of the slip conditions on the airfoil, which are a little bit unphysical. So with these high angle of attacks, the slip condition, ignoring the boundary layer, keeps the flow attached a lot harder than it normally would. But you can still see we do have separation in the flow here towards the bottom of the airfoil at this high angle of attack. So let's go back just to our standard airfoil at 10 degrees angle of attack. Okay, reload that. And then let that go. So that's a quick overview of how you can study and simulate airflow path airfoils at different conditions, different angles of attack, bomb layers or without a bomb layer, different angles of attack, different Reynolds numbers. It's a very quick overview of the kind of analysis you can do as a student to study airfoils and aerodynamics of airfoils using Digital Dynamics Studio. But the point is to give you an idea of what can be done and then go and experiment on your own. Go into Digital Dynamics Studio and reproduce the same kind of experiments that we just ran through here. And as we said before, if you go under documentation in the suggested experiments section, under the airfoil section, angle of attack, you can see some background information and all kinds of different experiments you can try and measurements you can take to do your own airfoil simulation experiments, plus other cylinders, vortex jetting, drag coefficients, Bernoulli's principle, heat convection, the flow between heated plates, all kinds of different things you can do with Digital Dynamics Studio to study numerical methods, fluid dynamics, all kinds of different things. So good luck experimenting on your own, and please let us know how it goes. We always want to receive as much feedback as we can about the tool and what students are learning by using it. Thank you.